Hello everyone, we are going to finish the 2019 NCEA Level 3 3.4 Thermochemistry examination paper today by finishing looking at question 3. So like always, if you have enjoyed these videos, find them helpful, please smash the like button, subscribe if you haven't, and share these videos with your friend. Alright, so let's get started. So question 3, so this is a very, again, if you've been grinding the old exam papers, you should be able to see this type of question, very common. So this is your typical intermolecular forces type of question. So you need to look at the type of molecules that you've been given, and it should be a little bit, now I'm not gonna just answer this question yet, but then let's just go through the 3 types of forces. Okay, so you have temporary dipole force of attraction. So temporary dipole force of attraction exists in all molecules. Okay, so temporary temporary dipoles force of attraction. So this exists in every single molecule. And what is temporary dipole force of attraction is it is formed due to random movement of electrons. So what that means, so just think about yourself. If you were a molecule, let's say right now you are neutral, okay, but then all of a sudden in your body, a majority of the electrons suddenly move to your left shoulder. So your left hand side will be slightly negative and your right hand side will be slightly positive, and that creates what we call a temporary dipole, because you have 2 opposite charges on the end of the molecule, so your left hand side and your right hand side. But this particular force of attraction is temporary because the electrons may decided, all right, we've had a good time on this side, let's just randomly move around to the other side, because their movement is quite unpredictable. So the temporary dipole force of attraction exists in all molecules. Okay, so you should have, regardless of what type of molecules you have, you should always put down temporary dipole force of attraction. And the temporary dipole force of attraction depend on one thing, which is the size of the molecule. So it depends, so I'm just going to make a little note here. So this depends on your molar mass. So the larger the molar mass, the stronger the temporary dipole force of attraction. So yes, it is temporary dipole force of attraction is the weakest type of intermolecular forces, but once the molar mass gets really large, this is actually quite a strong intermolecular force, because with more molar mass, that means you have more electrons. If you have more electrons, that means you create a stronger dipole. Let me give you an example. Let's say if I use the same example, if I have 3 electrons on the left hand side, 1 electron on the right hand side, so this is, you know, just random movement. So this is 3 electrons, this is 1 electron, so this is slightly negative. It's not the best drawing. That's slightly, this side is slightly negative, this side is slightly positive. Okay, but what if you have 30 electrons on this side and 10 electrons on this side? Then this is going to be slightly negative, this is going to be slightly positive. But can you see this slightly negative is going to be stronger than the slightly negative of the smaller molecule, because you simply have more electrons. The more electrons you have, the greater the difference of the charge. Okay, so that's one thing we need to consider. And then we do look at permanent dipole force of attraction. So permanent dipoles exist in polar molecules, and this, you need to be able to understand polarity. So if you don't understand polarity, I would recommend you to go back to question 1 and have a look at the polarity section, or I was planning to do a Lewis diagram and polarity section for the level 2s in the near future, so maybe you can go to that and watch it there. But this is a polar molecule, this is a non-polar molecule, and then you may ask, how did you figure this out? Well, just think of all the hydrocarbons, all the alkanes, alkynes, they're non-polar. Okay, they only have carbons and hydrogens, they're non-polar. But if you have like nitrogen bonding to hydrogen, if you're drawing a Lewis diagram, you should be able to draw an H lone pair up here, this is an asymmetrical shape, trigonal pyramid, don't cancel out polar. CH3NH2, same thing, CH3 bonding to NHH. Then this has a lone pair of electron up here, and that's that's polar as well. Okay, so this have permanent dipole force of attraction, and the other one also have permanent dipole force of attraction. The one in the middle doesn't. Okay, and the last one that we always talk about is hydrogen bonding. Hydrogen bonding is when you have, if I use the example of nitrogen and hydrogen. Oops. Sorry, a text just came on the phone, so I was distracted. Okay, so if I draw, so what is hydrogen bonding? So hydrogen bonding is when you have a hydrogen atom bonding to either N, O, or F, because these three elements are really electronegative. Right, so what that means, if you have this nitrogen and with the hydrogen is really delta positive because of its low electronegativity value, and then the nitrogen is very positive, very negative. Okay, so if you have this really strong positive charged hydrogen, and then can you see that these electrons are negatively charged from the neighboring nitrogen atom? So they will be like, hey, you're really positive and you're really negative, we should, you know, interact. And this particular force of attraction is hydrogen bonding. I really don't like the word bonding in here because they're not technically bonded together. It's more of a electrostatic force of attraction between the oppositely charged atoms of different molecules. So they're not physically bonded together, but that force of attraction is really strong, so they get pulled apart, they get pulled together. So this is what hydrogen bonding is. Okay, so you must have hydrogen bonding with NOF. So this NH3 has hydrogen bonding, this doesn't have hydrogen bonding, and then your nitrogen bonding to hydrogen, so this has hydrogen bonding as well. Okay, so I'll explain those in a little bit more detail. Using the data, you identify the molecule has the strongest force of attraction. Okay, just look at the boiling point. Which one has the highest boiling point will be the strongest. So that's that one, CH3 and H2. Okay, because it has the low, it has the highest boiling point. Don't get confused with the negative. The smaller the negative number, the higher it is. Okay, and justify why methylamine has the higher boiling point than ethane. Okay, so you can, in this case, normally they will give you a molar mass, the molar mass of the molecules. I mean, we can figure it out here. So C2H6, C is 14, C is 12. Then plus 12 plus 6, so that's 30 grams per mole. And then CH3 and H2, that's 12 plus 3 plus nitrogen from my head, top of my head is 14 plus 2. That's going to be 15, so that's going to be 31. Okay, so the molar mass is really similar. If they have really similar molar masses, that means the temporary dipole force of attraction is going to be very similar. But because methylamine is a polar molecule, it has hydrogen bonding, it has permanent dipole force of attraction. Hydrogen bonding is the strongest intermolecular force, so that occurs between the hydrogen, the very electropositive hydrogen, and the neighboring nitrogen's lone pair of electrons. So that's hydrogen bonding. This force of attraction is really strong, so you require more energy to break that. Okay, so if we look at the answers here, so methylamine have similar size, so what it means, they have similar molar mass, so they have similar number of electrons, so they have similar temporary dipole-dipole force of attraction. But because methylamine has hydrogen bonds, and you can elaborate on what it is, it's the strongest intermolecular force, requires the largest amount of energy, therefore has a higher boiling point. Okay, this type of question I kind of explained to this person in one of the comments in other videos before. Is this particular section you can literally learn these every single year. The questions are so similar. Just grind through them. If you didn't understand, then I hope my videos help. But if you just wanting more practice, you can just do the exam papers, look for the answers, and just get used to the wording. Okay. And why methylamine has a higher boiling point than ammonia. So if we again look at if you look at ammonia has a molar mass of 17 grams per mole, and the other one, what did we say is 31 grams per mole. Okay, so straight away for your methylamine, because both of these are polar molecules, both of these have hydrogen bonding, so they're in the hydrogen bonding and then polar and the permanent dipole-dipole force of attractions perspective, they are really similar. But because methylamine, you can look at the molar mass, it almost doubles the NH3. Because it has a larger molar mass, that means it has more electrons. It has more electrons, that means it will have a stronger temporary dipole-dipole force of attraction. So what it means, it makes the molecules more polarizable. So that means when it does move, when the electrons do move around, you will create a stronger temporary dipole force of attraction. So that means it has a higher boiling point. So I think it's a little bit nasty that they didn't give you the molar masses. I mean, they could have done that in the resource sheet. I don't know, I haven't seen the resource sheet, but it's hopefully it's obvious enough that the CH3NH2 is a bigger molecule, but or you can just I just memorize the molar masses because I use them too often. Okay, so if we look at the answers, so they both have hydrogen bonding, they both have an H bond, so they sort of cancel each other out. But the methylamine has a significantly larger molar mass, so it has more electrons, makes it more polarizable, resulting in stronger temporary dipole-dipole force of attraction, requires more heat energy. Okay, what more polarizable just means is that if more electrons means you can have the larger discrepancy between the number of electrons on the left and the right. You know, if you go back to the examples I gave you before, it just means that the more electrons there are, the greater the dipoles will, the stronger the dipoles will be. Okay, so it makes it more easy to be polarized. Okay, but I think this should be quite straightforward enough. Especially, I hope that if they give you the similar type of question, that they do provide you the molar mass. Otherwise, it could be a little bit tricky. Okay, so do grind these intermolecular forces type of question. They are guaranteed excellence questions in the NAV exams. So do go through them. Okay, now this type of question, this is again, I've done this in my Hess's law question video. If you got 3 enthalpy of formations, you don't have to do the Hess's law equation calculation that we did. Just remember the enthalpy of reaction equals the total of the enthalpy of formation of the products minus the enthalpy of formation of the reactants. Okay, so you just need to find these. So HCN, that and that. And why did I not highlight H2? Because H2 is an element. Enthalpy of formation by definition is the amount of energy required or released when you make a particular molecule from the elements. If I were to make an element from an element, there's no enthalpy of formation, there's no difference. Okay, so products, what's the products? HCN is going to be 135 minus the reactants, CH4 and H3, so just add those together, negative 45.9 minus 74.9, which is going to give you 256 kilojoules per mole. Very easy merit question. Okay, make sure you don't copy the signs incorrectly. Last one. Oh, this is looking at entropy. So entropy has been a new idea for a couple of years now. So just remember entropy and spontaneity. Spontaneity depends on two things. Okay, so this is the other excellence, but I think I'll probably spend more time here because this is where people get really confused with spontaneity and entropy. Spontaneous reactions depends on two things. If you have a negative change of enthalpy, it tends to be spontaneous. If you have a positive change of entropy, it tends to be spontaneous. If you have both of these, then it's always going to be spontaneous. And I'll go through kind of why that is. So if you think about negative change of enthalpy, yeah, let's just draw the heat diagram like that. So that's negative change of enthalpy. This is positive change of enthalpy. Okay, can you see? Look at the activation energy. Can you see this? This is the activation energy. Can you see this is the activation energy? Can you see the difference? I mean, it should be quite visible that it is much easier for a reaction that is releasing heat to be spontaneous because they have less activation energy requirement, and by releasing energy, they become more stable. I mean, you know, when I teach chemistry, you know, to year 9s and 10s, they always go, "Can we blow something up? Can we blow something up?" Because what is blowing up? What are explosions? Explosions are essentially a process of releasing energy. So why do things explode? Is that they want to release all of the extra bit of energy, so they want to be stable. That's why those particular really reactive, really explosive reactions, if you just give it and initiate a bit of energy, you'll kick off, because that's tend to be quite spontaneous that way. Okay, so that's how I tend to explain enthalpy change. If you look at entropy, they don't, you can try to think of it as the particles or the molecules, they don't really want to be held together, because the more disorder there is, entropy is a measure of disorder. Okay, so if you can just think about your, like, I mean, look at your bedroom right now. Is it really clean? If it's really clean, then it has really low entropy, very, very organized. Okay, and in the chemicals perspective, that is very, very undesirable, because they want to be free moving. In that regard, they will prefer a high disorder, so a positive change of entropy, so that means more disorder is more desirable. Okay, more random, more disorder is more desirable. And how you can look at entropy change, you look at the number of gas particles. So that's gas. This is 4 moles, this is 5 moles. So on the left hand side, you are dealing with 9 moles of gas particles, and on the right hand side, you are going with 10 moles of gas particles. So you're going from 9 to 10. So that means you are going from less disorder to more disorder. You have a positive change of entropy. So that's done. If you look at enthalpy value, that's negative. So that's done. So this reaction will always be spontaneous. Okay, so they want you to justify in terms of the entropy change. So they don't really need you to talk too much about enthalpy. So let's look at the entropy change of the system and the surroundings. So let's look at what it means. So this is where we're going to tie in some of the enthalpy stuff as well. So let's look at the system. The system we just talked about, you've gone from 9 moles of gas to 10 moles of gas. So the system means inside your reaction. Okay, so from 9 moles to 10 moles, the entropy increases, so that's desirable. And because the reaction is negative, the reaction has a negative enthalpy change, so that means this is exothermic. What does exothermic mean? That means you, in terms of heat, it means you release heat, doesn't it? Where does the heat go? The heat goes into the environment, doesn't it? So the environment, the particles into the environment, the particles of the environment, particles receive more energy, and when they receive more energy, what do? They vibrate, don't they? They will randomly, they receive more energy, they will move around more. If they move around more, is it more random or less random? And hopefully in your head you would have said more random. Okay, so essentially, if you look at the spontaneity of a reaction, the delta negative H means you are increasing the entropy of the surrounding. If you look at the equation, look at the system, the entropy is also increasing. So you have system increasing entropy, you have surrounding increasing entropy. So therefore, the total the systems and the surrounding entropy both increases. That will give you a spontaneous reaction. Okay, so just remember, I mean, this is one way I'll tend to get, because I'm trying to, especially when I try to teach this at the beginning, try to explain why enthalpy change is related to spontaneity. When I draw this diagram, people understand straight away. But then if you want to tackle this type of question, why does the entropy change, and link the entropy change to system and surrounding, you need to understand that if you have an exothermic reaction, you release heat. Where do they go? They go to the surrounding environment, heat up the particles, it will move around more, and they'll be more random. Okay, so more random just means more entropy. Okay, so here's a more NCEA from the marking schedule. So same thing that we talked about, 9 moles to 10 moles. So the entropy of the system increases. Because it's exothermic, it releases energy. So that means there's more disorder. So the entropy of the surrounding also increases. So both entropy increases, the reaction is spontaneous. Okay, you don't need to talk about Gibbs free energy. Someone do, the G equals that. There's no need to talk about those. There's some type of question are like these. If you have, I tend to give my students this table. If you have a negative change of enthalpy, positive change of entropy, this reaction is always spontaneous. If you have neither, if you have that, the reaction is never going to be spontaneous, because you have neither of the desired conditions. It's only when you have both negative or both positive that can be a little bit tricky. So this depends, maybe, this also depends on the condition, because this is the desirable, the negative delta H and the positive delta H, the negative delta H and the positive delta S. These are the desirable conditions. So it depends on the effect. So for let's say if I number these 1, 2, 3, 4, for the third combination, the reaction could be spontaneous if the negative change of enthalpies, if that quantity is significant enough to compensate for the negative change of entropy. That means you will have a more spontaneous reaction. Same thing for number 4. If you have a positive change of entropy in your system, which is significantly enough, which will compensate for the positive change of enthalpy, then it may be spontaneous as well. Okay, so temperature also helps. So just think about what this increasing or decreasing temperature does. Temperature tends to link to the entropy of the system. You can think of it that way. So if I have a positive change of entropy, positive change of entropy means if I link to the question that we just did, if I have a positive entropy, positive change of enthalpy means you absorb energy, yeah? So if you absorb energy, that means the surrounding system's entropy will be less, because energy has been absorbed and they don't move as randomly as we would. So how can we minimize that effect? You increase temperature. Okay, so if you do this reaction at a higher temperature, that will be more spontaneous. Why? Because this higher temperature will compensate for the energy absorbed, and that will minimize that effect. Okay, so the higher temperature minimize the effect of positive delta H, or you can say it maximizes the effect of delta S. So same thing here, but then it's different type of thinking. If I'm already releasing energy, that means if you have a lower temperature, the lower temperature will minimize the effect of the change of entropy. Okay, so just to go through this tend to be a magical like a magic paragraph that I tend to use. If you have, like, say 1 and 2, if you have the first one, it's always spontaneous. Number 2 is never going to be spontaneous, and the number 3, number 4, well, it depends. If the thing I just circled are significant enough to compensate for the undesirable condition, which is negative delta S and positive delta H, then the reaction will be spontaneous. Okay, so this temperature dependent. So you can I just tell people to remember that a higher temperature, think of entropy. Entropy is random movement. So if you have even a higher temperature, that will make the particles even more random. That's one easy way to remember. Okay, so hopefully this has been helpful. So that's the entire paper done, and hopefully you've learned something, and all the best with your exams. Otherwise, I'll see you guys next time. Bye bye.